Hello, everybody. It's a pleasure to be here. Switching over to the slides. So, the title of my talk today is Evolving Software for the Microservice and Serverless Era. For those of you who don't know me, my name is Graeme Rocher. I'm a software engineer at a company called OCI, Object Computing. And I created a couple of frameworks, Java frameworks, which some of you may have heard of. One of them is called Grails. Anybody heard of Grails in the audience? A few hands. And the other one is Micronaut, which is a newer product that's been out for a year or so. This year, I was privileged enough to be the inaugural Groundbreaker Award winner. So thank you kindly to the kind folks at Oracle for nominating me for and choosing me for that award. It was a remarkable privilege to be alongside 4 other Groundbreaker Award winners who I felt humbled being next to, the creator of Kafka and the creator of JRuby and all these amazing people. So yeah, do pay attention to that and become a groundbreaker yourselves. In this talk, what I'm going to be talking about is the challenges facing Java and software in general when looking at serverless versus traditional models. We'll look at some emerging solutions for this space, specifically Micronaut and GraalVM. And we'll do some code demos, because nobody likes death by PowerPoint, so we're going to do some demos, which I'm sure you'll appreciate. So in terms of serverless, serverless is a completely different architectural style, and there are challenges when you look at existing architectural stacks and moving them to a serverless or a microservice scenario. Existing tools are not really optimized specifically for serverless. If you think about the requirements for cold starts and low memory footprint. With things like serverless, typically your function is kind of kept warm by some kind of FAS system, whether it be OpenFAS or whatever, and executed, and then it's kind of put to sleep as kind of pay-per-use model. So cold starts become increasingly important. And this has an influence on the architectural decisions you make when choosing the technology that you want to use for developing serverless applications. So Go, Node, etc. Are typically better today in this regard than Java in terms of cold starts. And is that better? Less scratching? Yay! Problem with beards? No, never have one. So yeah, you have folks like Tim Bray, fairly influential chap, not recommending Java at AWS's conference. Crazy talk, in my opinion, but anyway. But it is true that we have to adapt, and you have to adapt. We have to adapt and think differently when it comes to serverless models. So, you have to optimize cold starts, like I said. You also have to, forget about traditional patterns. So, things like connection pools don't really make sense in functions. There's no point in storing a pool of connections in a function when, the function is going to go away and the pool has to be shut down. Local caches, in-memory caches, kind of become irrelevant. Traditional models in Java applications, we have all these local caches to improve performance, but if the process is going to go away, there's no point in retaining those local caches. And your technology influences are going to be influenced by your cold start requirements. Microservices, specifically with regards to deploying microservices into containers, is also influencing existing architectures. So cold starts maybe are less important, but still important in a container-based world in Kubernetes, where the container is the deployment model. But containers in Java require special memory management and special considerations when you define your Docker file or whatever. Java's memory model is adapting to containers today, and there's new flags available in the latest JVMs to make it work better with containers. But you have to think carefully about memory optimization with containers, and that's yet another consideration that you have to think about. And if you look at traditional Java frameworks, traditional Java frameworks, the popular ones, whether it be Jakarta EE or Spring, they are optimized and built 10 years ago for a time where we had big servlet containers where you would deploy your application that would be always running. And memory startup, not really particularly important in this scenario. And based on this design and the architectural constraints, the way they typically work is, if you look at how something like Spring works, for example, it actually reads your bytecode, your Java bytecode, at runtime. It will synthesize new annotations for you for each annotation in your code base to support what's called annotation metadata. And this is something that's done for every single bean in your application, and it will build large reflection caches because the way it's going to work out how your application functions is by analyzing your code base and looking at your annotations and so forth. For every bean, every method, every constructor in your code base. So, this situation has left us with kind of tough technical decisions because you have to choose the appropriate model for the job, and traditional frameworks like Spring, like Jakarta EE, are typically not the best choice for something like serverless. So the reality is that the micro reality, and if you're trying to achieve fast cold startup, fast cold starts, low memory consumption, is that frameworks that are traditionally based on reflection and analysis of annotations in Java become pretty fat pretty quickly in terms of memory. But Java developers love the programming model and the productivity that some of these tools offer. So we kind of live with it. But is there any kind of why can't we not be more efficient? Isn't there a way to be more efficient? So traditional frameworks, traditional Java tools, and so forth, there's typically this correlation in them between the number of lines of code in your code base and the startup time and memory consumption. So if you look at a typical Java application out there today in the wild, whether it be based on Spring or whatever it may be based on, as the number of lines of code go up, so does your startup time and your memory consumption. And wouldn't it be nice if we could break this correlation so that your traditional Java application didn't have to consume so much memory? Really, if you look at technology stacks in Java, in particular, you have really two groups of high product. You have these up in the top right corner over there. You have these technology stacks that typically are high productivity and opinionated, and these are the ones developers love. They're the most popular in the Java space stacks out there. Things like Spring, things like Grails, things like Microprofile. They provide more opinions, and they provide high productivity levels. And then in the bottom left corner, you've got like technology stacks, which are I like to call them your do-it-yourself toolkits, where you can kind of put together your application manually. And these are things like Vertex and Spark and Ratpack, and there's all sorts of little HTTP toolkits out there that do this. And they don't provide the same productivity. You have to kind of do a lot of manual decision making. They're not very opinionated, but they come with low memory consumption and startup time. And so you've kind of left with this choice with just existing Java tools in terms of either choosing low memory, but kind of having to do a lot of manual labor to get there, or or you go for one of the high productivity tools like Spring or Grails or Microprofile, and you end up with an environment that consumes a lot of memory, which is not necessarily the most appropriate when you're thinking about serverless or microservices in containers. So what is the cause of these problems, and why do you get folks from Amazon criticizing Java and unnecessarily? It's a popular thing to criticize Java. But there are some actual fundamental architectural problems in Java that make it difficult for framework developers and users to create applications that consume less memory. So the annotation API, for example, in Java is pretty limited in that there's annotations attached to fields, attached to classes, attached to different parts of the application. But there's no built-in way to query the annotations to find out what meta annotations are. There's no way to merge annotation data from interfaces and classes and fields and so forth. And it's really quite limited. You have to do a lot of reflective analysis on the annotation API to actually get a framework to do what you want it to do. Then you have things like type erasure. So, the JVM didn't have, Java didn't have generics before, and then generics were added later. And in order to support backwards compatibility with generics in Java, the actual types are erased. So if you declare like a field that is a list of string, at runtime that string is gone. That reference to that type is gone. It's not retained, and there's various interfaces and classes where you can kind of get access to it, but it's very difficult. Reflection is also pretty slow, and there's various ways in Java that you can improve that. And there's been some innovations over the years to try and make that better. Things like invoke dynamic and method handles and so forth. But fundamentally, for reflection, it's always going to be slower. And it's also very hard to do closed world static analysis on reflection because the more dynamic you make an application, the more difficult it is to optimize. Another major problem with in the Java ecosystem is reflective data caches. So every single library and toolkit out there seems to have like a unique reflective data cache. And it becomes a massive problem when you're trying to optimize memory. So for example, you have a reflective data cache for Spring, for all its reflection data. You have another reflective data cache for Jackson, for marshalling JSON objects and back and forth. So every time you marshal a JSON object with a class, say book, it's going to build out a whole bunch of reflective data and cache that data because you can't keep reading it, and it'll cache it in a map and so forth. And the way the JVM works is that as soon as you read a class via reflection, it stores a reference to the methods and so forth using soft references. Now, what soft references are is essentially they don't get garbage collected until your JVM starts running low on memory. So you have this retention on reflective data, and these reflective data cache, because each different library and so forth is restoring a unique cache. And reflection makes it very hard to build a low memory footprint application because of all these caches. Class path scanning is also a popular feature. Developers like to be able to just define their classes, run their app, and it just works and it finds all the classes and so forth. But to implement class path scanning effectively, you have to allow the running application to scan the classes of your application at runtime, looking for the appropriate annotations and so forth. And that makes it difficult to optimize startup if you're scanning and doing I/O or disk I/O to read the annotations of your classes. Class path scanning is really slow. And dynamic class loading can be slow. Not always. Depends how much or how often you're doing slow dynamic class loading, but it can certainly be slow. And dynamic class loading also impacts how easy it is for ahead of time compilation tools to optimize your application your application. So a question I often ask people is, if, when the Kubernetes developers decided to build Kubernetes, if they had built Kubernetes using Spring or Jakarta EE instead of Go, which is becoming an increasingly popular language because of its low memory footprint and so forth, what would have been the result? So you have Docker and Kubernetes running locally, which are each of which are made up of a collection of microservices. Many of you probably have these systems running locally on your laptops, yeah? And the remarkable thing about these things is that they run locally on your laptop, Docker and Kubernetes, but they don't need you to have one of these as a laptop, yeah? Because fundamentally, Go is consuming very little memory, so you can have a whole suite of microservices running locally, and it doesn't require you, each and every one of us, to have a supercomputer to run it. And that is based on a technology choice of choosing Go at the time instead of a traditional Java framework. Having said that, Java's problems are also greatly exaggerated. People have been saying Java has been dead forever, which, every time something new comes out, Java's supposedly been dead. Ruby on Rails came out. Oh, this is going to kill Java. Node came out. Oh, this is going to kill Java. Java's been dead. If you listen to people out there in the audience, Java's been dead for like 20 years. And fundamentally, it's complete nonsense. And the reality is that Java can be fast, and it can consume little amounts of memory. This has been proven time and time again. Have a look at Android, for example. Android has the same requirements as serverless, if you think about it, and microservices in terms of you want that app on your Android phone to start up quickly. You want that app on your Android phone to consume a little amount of memory, yeah? And I'll talk about Micronaut in a minute. But, in order to achieve that, you've got to look at the tool set that you're using to build an application. Most existing tools for Java, and certainly the popular ones, are based around fundamental principles, which are the use of reflection, the use of runtime proxies, the use of runtime bytecode generation, whether it be bytecode, ByteBuddy, or CGlib, or something like that. And these are the things that lead to problematic memory consumption and problematic runtime performance. And Java has many, many, many advantages over other languages. It's a mature, robust ecosystem. It's got outstanding IDEs and development environments, and not just one. You got so many of them. From IntelliJ IDEA to Eclipse to even Visual Studio Code now supports Java. It really has so much. Code maintenance and refactoring. Like, Java developers take it for granted, but just being able to open up a class, rename a method, and have that refactoring propagate to the whole code base, that confidence of being able to change and maintain a code base and evolve it over time is not something that's just there for other tools and technologies. Developer availability. Look at this audience here. Most of you, I imagine, know Java. There's Java developers everywhere. Build system maturity. So, Maven and Gradle and the Maven Central and the whole build ecosystem around Java is light years ahead of other technologies when you consider things like the battles that NPM and the Node community have gone through to get stable build tools and so forth. Diversity. So Java is so diverse. It's used in mobile, IoT, server side. It's not just serverless. It's not just it's not just microservices. Java is broad and diverse, and diverse also in terms of the languages that it's able to run. You got amazing set of languages that run on the JVM today, from Java to Kotlin to Groovy to Scala Closure as well, which I don't have on the list, but there's a whole, even JavaScript runs on the JVM. So, it has a very rich ecosystem that, is beyond anything else out there. Another thing I like to say is, and I've heard a lot of people say as well is, by the time a language like Go has all the features of Java, Java's startup performance will match Go. In 2021 or 2022, by the time all of those things happen. So, and the other thing I would say is, optimizing Java and optimizing Java applications is an already solved problem. Yeah, I brushed on this before, but the server-side Java community has a lot to learn from the Android community. Android uses ahead-of-time compilation extensively to make sure that that Android app that you have running on your phone is as memory efficient, as fast, and starts up as quickly as possible. They have tools such as Google Dagger, which is a compile-time dependency injector, which is reflection-free. It's limited in scope to just EI, but it allows you to build applications, use dependency injection, all reflection-free. And Android makes extensive use of annotation processes to pre-compute as much as possible, as much as the application as possible, so that by the time it's running on the phone, it's as optimized as it possibly can be. So I just mentioned this word. What exactly is ahead-of-time compilation? Well, ahead-of-time compilation is, if you speak to the folks at GraalVM, which I'll talk about in a moment, it's, the pre-computation of application code into native binary using closed-world static analysis. Now, that sounds very, very complicated. I don't know about you, but that's a bit of a mouthful. But basically, all it means is, it's a fancy way of saying is, let your compiler do the work at compile time so that at runtime your application is more efficient. Yeah? And with that, I want to introduce the product I've been working on for the last year and a half or so, which makes use extensively of ahead-of-time compilation. So Micronaut is a new way to build applications for the server side that uses ahead-of-time compilation to pre-compute your application requirements. At a high level, Micronaut can be thought of as a microservice and serverless focused framework, hence the branding, Micronaut. But it's also a complete framework for any type of application. Whatever type of application that you want to build, whether it be a CLI app or whatever, you can build with Micronaut. The difference between Micronaut and a traditional framework, traditional Java framework, such as Spring or CDI or Jakarta EE, is that everything, all the dependency injection, aspect-oriented programming, AOP advice, configuration management, etc., bean introspection, everything is done at compilation time. So it's moved the job of the framework infrastructure from the runtime part to the compiler. Yeah? Micronaut uses extensive AOT compilation, ahead-of-time compilation. So all of your dependency and configuration injection is computed at compilation time. All of the annotation metadata, so it'll pre-calculate from your classes all of your annotations, like meta annotations. So for example, if you have a @transactional annotation and that transaction is present on another annotation, it'll pre-compute the annotation hierarchy and figure it all out for you. It pre-computes AOP proxies. So, if you define, again, the @transactional example on a service, it'll, instead of relying on runtime proxies and runtime bytecode generation, it'll do that at the compiler level so that when you compile your application, it's a fixed set of classes and there's no dynamic class loading all framework infrastructure is pre-computed. Essentially what Spring and CDI do at runtime. So with Micronaut, you can build a whole bunch of stuff. You can build microservices. You can build serverless applications. You can build completely headless, without an HTTP server, message-driven microservices with Kafka or Rabbit MQ. You can build command line applications. And yes, you can even run it on Android because we're efficient enough to be able to support running on Android. Anything with a static void main, you can build with Micronaut. So what is Micronaut really? I like to think about it as an application framework for the future. It's a set of building blocks that inspire best practice such that you can build memory-efficient applications on the JVM. So it uses no reflection. It's completely reflection-free. It uses no runtime proxies. There's absolutely no dynamic class loading. All class loading requirements are pre-computed at compilation time. It has an extensive API to do ahead-of-time compilation for other things. For example, one example of that is we have support for Swagger, which is open API, and it'll actually pre-compile your Swagger information at compilation time rather than waiting to do that at runtime and then consuming more memory. And of course, it lets you build microservices. So Micronaut is pretty new. We open sourced Micronaut in May 2018, so it's been 9 months. And the impact it has had on server-side Java has been remarkable to see over the last 9 months. And it is really inspiring a complete shift in the industry. It sparked massive improvements from big companies like Red Hat with Quarkus, which is takes a similar approach by pre-computing your application requirements. And it's inspiring Pivotal to improve Spring Boot's memory efficiency as much as possible and startup time. And it's really created a massive impact and really put the focus on the industry of server-side Java to improve for the serverless and for the microservice use case. And now I want to talk about another technology that is up and coming as well and is also very much based on ahead-of-time compilations. So GraalVM, who in the audience has heard of GraalVM? Yeah, a few hands here. So GraalVM is a new universal virtual machine from Oracle Labs. And it's currently at kind of release candidate beta stage right now. And it does a whole bunch of things. So it's kind of a replacement for the JIT in Java in Hotspot. And it also features a language framework called Truffle. It has implementations for Ruby and Python, and it allows you for languages to interoperate with each other. So for example, a Java application to call a JavaScript application and so forth without any overhead in terms of communicating and type conversion and so forth. It also has another feature, one specific feature, which is just one part of GraalVM. The actual suite of GraalVM tools is enormous. But it has a native image tool that allows you to convert Java code, Java bytecode, into a native machine image using ahead-of-time compilation. And why would you do this? There's some disadvantages to doing this. When you do this, for one, the compile times are quite long, and you lose certain features like write once, run anywhere, and you lose things like the JIT compilation. But what you do gain is remarkable optimization in terms of startup time and memory consumption. So, for example, with Micronaut and GraalVM, the startup time for a microservice is 20 milliseconds, which for a Java application is quite remarkable. Also, memory consumption. I actually think that we put some more optimizations in. It's actually down to 14 meg the last time I checked. So the actual native image, when you run it, only occupies 14 megabyte of memory, which is pretty remarkable when you consider, a traditional Java application. Even with Micronaut, we're looking at around 70 megabyte of memory. So with that, I'm going to do some demos and show you some of the stuff I've been talking about, and we'll see how it goes. So, so I've got over here a Micronaut application, and what I'm going to do is I'm going to go into presentation mode. There we go. And this is a Micronaut application, and you can see it has an application class which you can run. And if I run this application inside my IDE, you can see that startup time is pretty quick, 945 milliseconds startup time, which is a lot faster than your traditional Java application. And the important thing is that as the application grows, because we're pre-computing everything, the compilation time doesn't get slower. The startup time doesn't get slower, sorry. So what I'm going to do is I'm going to further this demo, I'm going to create a controller, and this is going to be a kind of a web controller, and we're going to just do a little hello world demo. And what I'm going to do is create a person that I want to greet, and they're going to have a name. And we can generate some getters and setters. So one of the things that one of the features of Micronaut is, and one of the challenges with Java, which I mentioned before, is annotation metadata. So what does that mean? In a traditional Java framework, one of the things that you can do in Java is you can define annotations on a Java bean either on the field or on the getter. That's the rule that it implies. So for example, if I wanted to apply some validation constraints, you could apply not blank over there, and you could say size on the method, and the maximum size should be 100 or something like that. And you can see that I now have a problem. As a framework developer, I have a problem. Because in order to compute this annotation metadata, I have to merge, first of all, I have to look at the method, which is public. And I can see that it's got a size constraint. Okay, that's great. But now I also have to reflectively access the private field to check the additional annotation metadata on the field, and I have to merge those together somehow at runtime. And in order to get the field, notice how the field is private. So the field is private, so I have to disable, the Java's private reflective access, set the field to accessible to get it. Breaking encapsulation, potentially the module system as well, and all of that just to analyze what this class is doing at runtime. Yeah. With Micronaut, I can add introspected to this, and what that does is compute all of that annotation metadata and bean access at compilation time. Yeah. And that's what I'm doing here. Then I can say I can create a greeting response, and it's going to have some text, and we can generate a getter and a setter. There it is, and we can create a post action that just submits the same URL and returns a greeting, and we're going to greet a person like that. And what we're going to say is we're going to create a new greeting, and we're going to set the text of the greeting to be hello plus person.getName, and we're going to return the greeting. So that's my simple controller action. I'm going to add introspected to this as well. Here we go. And basically what it is it maps to the greeting URI, takes a person, sets up a greeting, and returns the response. So how would I test this? Let me write a quick little test. And it's going to be a greeting controller test. And we're going to make this a Micronaut test. And it's going to test my controller. And one of the nice features of Micronaut is you can create clients that are interfaces that are pre-computed at compile time. So I'm going to create a client that's an interface. And we can just copy this. You can actually share a parent interface if you want. And then I'm going to inject that into my test. That's my client. And I'm going to say greeting client, greet, new person. Greet the person. And that's going to give me a greeting response. And then we're going to say assert equals. Hello, John. Greeting.getText. And we may want to set the name of the person before we send it off, otherwise you're going to get a validation error. John. So let's run this test and see what happens. And if the demo gods are with me, we may get a result that is, the test passed. And now look at that. That test executed in 510 milliseconds, right? This is not a mock. This is not a pretend test. There's no mocking. If you don't believe me, we can go into my logback file here, and we can add a new logger. That is io.micronaut.http, and set the level to be trace level logging. And we can run that test again. And you'll see that the test is now outputting my logging, and you can see it's spinning up the server, it's creating a new server, it's sending a request, it's receiving a response. At no point am I mocking everything. This is your real functional test executing your real code. And I think this is one of the revolutions that Micronaut is creating, is that you no longer have to have special mocking APIs to mock out your server that takes 10, 20, 30 seconds to start up. You can just write your unit tests are fast, and so are your functional tests. My functional tests are remarkably fast. So I can execute that, and it sends a request to my controller, receives the response, and I get it back. Now, that's my application done. If I want to build this into an actual kind of working application, how do I do it? So I can say Gradle wassemble, and we support Maven as well, so you can build that into a Maven project. And then you can just run it as run the microservice as a regular jar file, and it starts up really fast. So if you want to then take that to the next level, you can, at the moment I'm using, what am I using? I'm actually using Graal as my JVM. You can build this into a native image. So I can say native image class, I'm going to disable the server, and I'm going to say this is I want to build a native image from my application. And this is what I was talking about with GraalVM compile times, is this process will actually take a little while. It might take several minutes, a couple of minutes to complete, but this is going to compute my application into a GraalVM native image, that has essentially an embedded JVM and so forth. And it's doing what the GraalVM team calls closed world analysis, static analysis of the application. And this works really well when there's no reflection, no runtime proxies, no everything, because you don't have to. GraalVM doesn't. It supports reflection. It supports runtime proxies, but you kind of have to tell it ahead of time where those things are, and that makes the whole process more complicated. While with this, because Micronaut is not using any reflection, it's not using any runtime proxies, it's far more efficient and can build a native image into, make building a native image a lot easier than your typical technology stack. So, as you can see, it's still compiling. This is definitely moving your work into your compiler. Your compiler is going to take a lot longer. It's converting this into a machine image that will only actually work on this Mac. So that's an important consideration. When you build your native image, you have to build it for the target environment. And yeah, essentially, once it's done, which I think it should be in a minute, you will have what's called a greeting service. There we go. It's built. So now I can just run my greeting service, and look at that. The service is up. Startup time is 26 milliseconds. If I look at top for my process chart, you'll see that my greeting service is this guy here, and you can see that it's consuming 15 megabyte of memory, consuming very little memory, and it's essentially the same application, but computed with GraalVM. So GraalVM is really a promising technology, and to keep an eye on. The technology is still very much in beta and experimental, but it's one of the most exciting things that are happening in Java right now. Micronaut optimizes for GraalVM, but it also optimizes for regular Java. So whether you use GraalVM native or not, it's all Java. You're still getting memory benefits. I had another little demo, which I don't know if I have time for, but it's basically a serverless function, which is over here, I think. Let's see. And yeah, this guy is a serverless function, which you could deploy to Project FN as a Docker image, and it shows the cold start performance of Micronaut with regular Java when building functions. So if I zoom in a bit, there we go. So if I execute this function, you can see that when I execute it, it's really fast, even for a regular Java function. The cold start time is really low. If I open this function up in an IDE, you can see the implementation, and it's very similar to that microservice that I just showed you, except this is a function. So I have a greeting function that executes a greeting. It uses dependency injection to inject the greeting service into the function. So it's using DI and everything, and the whole thing executes very, very quickly. I have a test that also runs the function and tests it out locally, so I don't need to deploy it to my target environment. The function itself is just a normal bean that extends function initializer in Micronaut, receives a greeting service, and calls person. And just by building that, I can build the application into a regular Java application, and I can pipe using Echo the input into the application, and it will read from system in and write to system out, which will allow you to deploy to many function as a service systems, whether it be Project FN or OpenFAS or any of the popular FAS systems. So Micronaut and microservice cold starts in memory. So in OpenJDK, you're looking at 800 millisecond startup time for Java. And memory consumption, you can specify a maximum heap of only 10 megabyte to run a Micronaut app. It's around about 100 megabyte, probably a little bit less depending what you're doing to run a Micronaut microservice as a minimum with OpenJDK.
Both OpenJDK and Eclipse OpenJ9 have an interesting feature which has a lot of potential for serverless and microservices, which is called class sharing, class data sharing. And what it allows you to do is, using AOT, pre-compute your classes so that when you start up your app, it's using like kind of shared classes that are already jittered, already pre-computed. And if I use that feature with Eclipse OpenJ9, and there's an equivalent feature in Hotspot, although it's a little bit more complex to use, Micronaut startup time goes down to 300 milliseconds, and the memory consumption is only 70 megabytes. In the Graal native scenario, when you convert your Micronaut application to Graal native image, what you have is a cold startup time of only 20 milliseconds, which is just crazy, and 15 megabyte of overall memory, which is pretty awesome. And in the cloud function scenario, a simple function, pure Java, is about 300 milliseconds cold start. If you, some function as a service systems use something called API gateway, and in that scenario, it's around 800 milliseconds. And if you involve Graal in your function, obviously that drops even further. Sometimes as low as 150 milliseconds. Obviously, with a serverless function scenario, it's a little bit higher because it has to spin up the actual machine or the container or whatever it is to get it operational. So, in summary then, Micronaut and GraalVM are leading the ahead-of-time compilation revolution on the server side. Server-side Java itself is adapting to the serverless world, where and microservice world, where cold starts and so forth are becoming more and more important. And contrary to popular belief, you can build efficient applications right now just through making framework choices that are the right way. And AOT sacrifices compilation speed to gain so much more, but it has the potential to completely revolutionize server-side Java and opens the world for going native with GraalVM in the future. So thank you very much. That was my presentation. If anybody has any questions, I'll be around at the conference all day. Happy to answer them. Thanks a lot.